You've probably heard this one before. Ice is slippery because there's a thin layer of water on top. Makes sense, right? Water is slippery, so if there's liquid on top of the ice, of course you'd slide. But here's the twist. That explanation, while popular, doesn't quite hold up. In fact, ice remains slippery even at temperatures far below freezing, where no melting should happen at all. So, what's really going on? Let's test your intuition. Picture this. You're on an ice rink wearing regular shoes. You step onto the surface and whoosh, you slide like a cartoon character. But now imagine that exact same temperature, say minus 20 degrees Celsius in a freezer. You touch a frozen metal tray or a block of frozen steak. It's not slippery at all. So why is ice different? Why does it stay slick even when it's solid, dry, and freezing cold? This question has stumped scientists for over a century. Even famous physicists of the 1800s debated it. Some thought pressure was the key. The idea was that when you step on ice, the pressure under your foot lowers its melting point, causing a thin layer of water to form. Elegant idea. But there's a catch. You'd need a lot of pressure to melt ice just from standing on it, more than your shoes could ever provide. Plus, skaters glide on ice even in temperatures where that pressure effect shouldn't work at all. So if it's not pressure and it's not just ambient temperature melting the surface, what is it? The answer lies deeper, in the strange behavior of ice molecules right at the surface. And to understand it, we need to zoom in, way in, down to the molecular level. Because what makes ice slippery has more to do with vibration, disorder, and a kind of microscopic dance, one that never stops, even in the deepest cold. Let's zoom in to where things get weird, right at the surface of the ice. Deep inside, the molecules of ice are arranged in a beautiful crystal lattice. They lock together in a stable, repeating structure that gives ice its solid shape. But the very top layer? That's a different story. At the surface, the molecules aren't fully bonded. They're at the edge of the structure, exposed to the air, and that changes how they behave. They wiggle constantly. Even in freezing temperatures, these surface molecules vibrate more freely than the ones beneath. They don't lock into place, not fully. It's like the ice has a layer of jittery, half-connected atoms that never quite settle down. Now here's where it gets cool. Literally and figuratively, this restless layer is what scientists call a quasi-liquid layer. It's not water in the usual sense. There's no puddle, no flowing, but it's not completely solid either. It's more like a ghost of liquid, hovering right on the edge of existence. Imagine a crowd of people in a stadium, all sitting quietly in their seats. That's the bulk of the ice. But the people in the front row? They're leaning forward, chatting, stretching their arms. They're still in the stadium, but they're less locked in. That's the surface of ice. This quasi-liquid layer is incredibly thin, just a few molecules thick, but it's enough to reduce friction dramatically. It acts like a lubricant, even though there's no actual melting. And here's the amazing part. The colder the ice gets, the thinner and more fragile this layer becomes, but it doesn't completely disappear. That's why ice remains slippery even at extreme temperatures, like minus 30 or 40 degrees. In fact, some experiments suggest that this slipperiness may peak at certain sub-zero temperatures depending on conditions like pressure and crystal orientation. So we're not sliding on water. We're sliding on an atomic anomaly, a strange surface phase that exists because the molecules at the edge are restless, unbalanced, and full of energy. They can't let go, but they can't hold still either. This subtle in-between state creates the low friction effect that makes skating, curling, and slipping on sidewalks possible. And it turns out, this behavior isn't unique to ice. Other materials show similar effects at their surfaces, but with ice, the effect is dramatic enough to feel under your feet. And now that we've uncovered the real source of slipperiness, it's time to ask, what else is going on under the surface that we've misjudged for years? Because this story of ice is just one example of how physics hides surprises in places we think we understand. Let's make this even more intuitive with a simple analogy. Imagine you're walking across a dance floor that's perfectly still. No music, no movement, just silence. That's like walking on a dry, frozen surface like metal, lots of friction. Your shoes grip. Now imagine the music starts playing, but only for the people at the very edge of the floor. Just a few dancers swaying gently, moving just enough to shift under your feet. The rest of the floor stays still. That tiny patch of subtle motion, that's what the surface of ice is doing. Those top layer molecules are dancing even when everything beneath them is locked in place. And that little dance party, just a few molecules thick, is enough to make you slip. This explains not only why ice is slippery, but also why its slipperiness is so special compared to other cold surfaces. It's not about water, it's about motion at the microscopic level. And here's the part that really makes scientists excited. This quasi-liquid layer isn't just a curiosity, it's a window into how matter behaves when pushed to the edge. Because on the surface, the rules change. Atoms become more unpredictable. Bonds stretch and twist in ways they can't inside the stable structure. It's like nature relaxing the rules just a little, right at the boundary. And that leads us to a bigger idea. In physics, surfaces are almost always stranger than what lies beneath. Whether it's the surface of a star, the edge of a black hole, or the skin of a soap bubble, weird stuff happens where one phase meets another. With ice, that weirdness creates a slick, invisible layer of looseness that we feel underfoot but can barely detect with our eyes. In fact, scientists didn't fully understand this until relatively recently. It took powerful atomic force microscopes and high-speed spectroscopy to catch the movement in action. Only when we could look close enough did we see those surface molecules jittering. Their bonds half formed, their energy always in motion. And the more we studied it, the more we realized this is not just a quirk of ice, it's a universal pattern. The edges of things, the places where order meets chaos, are where the most interesting things happen. So next time you see someone slip on an icy sidewalk, or you glide across a skating rink, remember, you're not sliding on water. You're skating on restless molecules that never fully commit to being solid. A slippery state between two worlds. And that strange in-between, that's where nature hides its coolest tricks. So what does this all mean in the real world? Why does understanding this strange jittery surface of ice matter beyond a cool trivia fact? Because it turns out, knowing how slipperiness really works helps us design better everything, from winter tires to Olympic skates. Engineers and scientists have taken this molecular insight and used it to fine-tune surfaces, adjust friction, and even develop materials that imitate the slipperiness of ice without being cold or wet at all. It's called biomimicry, copying nature's tricks to solve human problems. And in this case, we're learning from frozen water. Let's take ice skating as an example. Professional blades are shaped in a very specific way, not flat, but curved with sharp edges. This shape maximizes contact with that quasi-liquid layer, letting skaters glide with precision and speed. But even cooler, modern speed skates are tested at different ice temperatures to find the perfect balance of surface mobility. Because too cold and the layer is too thin, not slippery enough. Too warm and it turns to liquid, adding drag. That sweet spot exists only because of the strange behavior of those surface molecules. And it's not just sports. Scientists studying glacier movement also rely on this same understanding. Glaciers slide over rock in part because of this quasi-liquid layer on the ice at the base. It changes how entire landscapes evolve. It's not just gravity pulling the glacier, it's physics unlocking the surface. That means our predictions about sea level rise, erosion, and climate patterns all depend on understanding how friction works on frozen water. A few nanometers of slippery molecules can shape the world. Even robotics benefits from this knowledge. Imagine designing a robot that can walk on ice without slipping. Now that we know it's not about puddles of water, but about atomic motion, engineers can create special materials that mimic the way human feet adjust to micro movements, countering slip before it happens. Grip, balance, and stability can all be optimized once we understand that the challenge is not ice as a whole. It's the topmost layer and how it dances. And here's the most fascinating part. The more we look at materials at the surface level, the more we find that slipperiness is often not about liquid at all. It's about disorder, about chaos, about atoms not sitting still. That means ice isn't unique. It's just the most dramatic example of a broader principle. What feels smooth, slick, or dangerous under our feet may actually be nature's way of letting energy escape at the boundary. A silent compromise between order and motion. And we're only beginning to understand how to use that to our advantage. So let's bring it all together. Ice isn't slippery because it's wet. It's slippery because its surface is alive, not in the biological sense, but in the atomic sense. Even in deep cold, the very top layer of ice molecules can't sit still. They jitter, vibrate, and twist just enough to create a strange, ghost-like slickness. This ultra-thin layer isn't liquid, but it behaves almost like one. Not because of melting, but because of molecular freedom. It's not water, it's energy, trapped at the edge of order. That's what makes you slip. And what began as a simple question, why is ice slippery, turns out to be a doorway into a world of invisible motion, hidden structures, and phase boundaries. It reveals that nature doesn't always follow clean binary rules. Sometimes it blurs the lines between states, and those blurred zones are where the magic happens. The quasi-liquid layer on ice is one of those magical regions. It's tiny, but its impact is massive. From figure skating to glacial movement, from designing winter gear to understanding the dynamics of atoms, this surface layer is a reminder that what happens at the edge can shape everything in the middle. So next time you slip on a sidewalk or glide across a frozen lake, remember, you're interacting with a physical phenomenon so subtle, it took scientists a century to figure it out. And you felt it, not with instruments, but with your feet. That's what science is. The hidden logic behind what we experience every day. And sometimes understanding that logic doesn't just help us walk better, it helps us see the world in an entirely new way. If this journey into frozen physics made you say, wait, what? Then imagine how many other everyday wonders are just waiting to be explained. Hit that like button if you learned something new, share this video with someone who still thinks ice is just cold water, and subscribe to How It Actually Works, the channel that gives you the key to understanding the invisible forces that shape our world, one curious question at a time.